Good evening. My name is James Wright, and I am an Associate Professor of Music and Supervisor of Performance Studies in the Department of Music and the School for Studies in Art and Culture. It is my very, very great pleasure to welcome you to this evening's lecture, The Physics of Harmony in Music, by our distinguished guest, Dr. Peter Grünberg. Tonight's lecture is sponsored by the Faculty of Science, and it is the second public lecture of the 2012 academic year. In fact, yesterday evening, the first lecture of the year was also presented by Dr. Grünberg, an inspiring way to begin the semester. Dr. Peter Grünberg is a renowned physicist from the Institute for Solid-State Physics at the Jülich Research Center in North Rhine-Westphalia, Germany. In 2007, he received the Nobel Prize in Physics, together with Albert Fert, for his work on giant magnetoresistance. I must say that it is with a good deal of Carleton pride that I feel compelled to mention that from 1969 to 1972, Dr. Grünberg was a postdoctoral fellow in the Department of Chemistry at Carleton University under the supervision of Dr. Arnold Königstein. Dr. Königstein joins us in the audience this evening, and he has been a key player in making this lecture come to fruition. Thank you, Dr. Königstein. Dr. Grünberg's musical interests are broad-ranging, but he has taken a particular interest in theoretical frameworks that have arisen throughout history to account for the phenomenon of consonance and dissonance. Analyzing the connection between music and physics, he has focused primarily on a universal question, one of music theory and psychoacoustics, namely, why do we have a feeling of warmth when we hear certain kinds of music, and why do other kinds of music give rise to feelings of aggressiveness or tension? Dr. Grünberg theorizes that the answer to these questions lies largely in acoustic factors relating to the overtone series and the harmonic partials that can be examined with the aid of Fourier analysis. This topic has led to inquiry in multiple disciplines in recent years, with applications in areas as diverse as signal processing, quantum mechanics, and neuroscience. This evening, we are delighted that Dr. Grünberg will be joined by his partner, soprano Keiko Hibi, who will provide live musical examples as Dr. Grünberg elaborates upon his notion of the relationship between music and acoustics. Welcome, Keiko. Keiko Hibi is a professor at the Toho College of Music in Tokyo, Japan. She has studied at both the Tokyo College of Music and at the Stuttgart College of Music, and she has recently come to wider attention due to her strong performances at prominent international vocal competitions, such as the ARD competition in Munich, the Maria Callas competition in Barcelona, and the Mendelssohn competition. Keiko Hibi has recently released a CD of 19th century German art song titled The Song I Love. Please join me in welcoming Dr. Peter Grünberg and soprano Keiko Hibi.
Well, ladies and gentlemen, maybe it's the time now. I can get started. I thank you for your interest in this topic. I ran into this topic for the first time when I was a Boy Scout and played the guitar, and often was asked to accompany a song on the guitar. And then very often you run out of possibilities what kind of chord you should take. That held me occupied for some time, and I never could solve the puzzle until about 10 years ago. I started to look again into this topic, and I was lucky to get also a so-called contra guitar, bass guitar, with many bass strings. Such things are even more important, that you do have a proper accompaniment. So now, meanwhile, the puzzle has been solved a little, but we ran into many other questions. I'm very happy that I met Keiko Hibi, who was all the time already very interested in that topic. So we decided to do that together. And also we decided that we would like to open the lecture today here with a song which we might also sing all together. But please pay attention in particular to my chords which I play, and find out if you think they are right always, or maybe they are not right, and then you might as well protest. Raise your hand if you think this is a wrong chord. I don't agree with that, and but please, no eggs or tomatoes. Just a protest is enough. We picked the song My Bonnie's Over the Ocean. I think well known to many of you.
My bonnie lies over the ocean. My bonnie lies over the sea. My bonnie lies over the ocean. Oh, bring back my bonnie to me.
Okay, some of you noticed something, right? Oh, let's try again.
Oh, bring back my bonnie to me.
Let's even worse, I think. Okay, another try.
Oh, bring back my bonnie to me.
Okay. So, the point what I want to make here is that not we all here in the audience, although already here we probably have different background in music and different education and used to different sounds, but nevertheless we for these chords we agree that there is only this solution which I played in the excuse me, I played in the end, and if we go worldwide, then this is even more so. Eskimo would judge in the same way, and Africans would judge in the same way. So these seem to be common rules you have to obey when you play this kind of music. It's like, although as if there are a mathematical formula from which you can calculate which is the right chord, and so. And I would like to give you an introduction to this topic. What is the explanation for that today? So now I then switch to my laptop, and we can start with a lecture that was only an introduction. So the menu which I would like to present you then, I can take that mouse here, yeah, right. I see. We'll go through tones, intervals, chords, cadences. We'll touch consonance and dissonance, and in particular for the explanation of consonance dissonance, I'll use the theory developed by Hermann von Helmholtz around 1850 that was. And then we will come also to sonograms and speech recognition, and finally a voce vista if time allows, because these latter topics, sonograms, speech recognition, have all something to do with higher harmonics and Fourier analysis of sounds, from which you can then formulate and derive, so to say, a language, a computer language, by which your computer can write down what you say. That is the speech recognition technique, very helpful. Maybe you have seen that I have a slight tremor in my hand, and I appreciate, in fact, very much that there is also speech recognition now, and I can use a typewriter and a computer. So let's go to the topic now. Yeah. So I would like to give you 4 samples of sounds. One is the recorder. Yeah, we forgot our recorder, I noticed at the moment. But you all probably know a recorder, how a recorder sounds. And this is the sine wave, no, not sine wave, the wave which is produced by a recorder in time. Then we go to a tuning whistle. I should maybe say in more detail what we see. So the original recording on the screen of my computer was this one, which you see here, which indicated by the mouse of the recorder. But to get a better picture, a clearer picture what is really going on, one can electronically or on the computer stretch this trace which you see here. So that is the original trace on the recorder. When you stretch that in time, then you get this almost sinusoidal wave, and it's typical for a recorder because in the recorder essentially only the air column oscillates. In that case, we very often get oscillations which are almost pure sinusoidal oscillations. Then at the second example, you show a sound from a tuning whistle. This, in fact, I can demonstrate to you. So, for example, this one is one. There aren't any. So, for example, that when you record that, and display it, then you see what is seen here. No, here. And when you stretch that in time, you get what is seen here. So these are all periodic oscillations. After one wavelength of the oscillation, it repeats itself strictly, it repeats itself again and again and again. And now there is a law found by Fourier, a Frenchman, mathematical Frenchman, that in that case, when you have such periodic functions, you can describe them by a series of sinusoidal functions, and the frequencies of the individual sinusoidal functions are equidistant from each other. That is in fact shown in, oh yeah, I should also mention the guitar here because we took that picture. So this one here is the trace of the guitar. The intensity trace when you pick the guitar and wait in time, then the amplitude decays, as you can see. So here we have this decaying amplitude. For the others, the excitation is you blow the recorder, then the amplitude in that case is for some time constant, and in the same way the tuning whistle is not attenuated in time so much as we see for the last example, where we pick the guitar and excite it at one point in time, and then the amplitude decays. But when we have a shorter range and then again extend or stretch the scale, then we get this kind of wave as you can see here. Okay, so all these are then these periodic functions, and all of these are also described by the Fourier theorem, which means that this oscillation can be decomposed into a whole series of sinusoidal oscillations, each decorated with its own amplitude. And examples for that for these cases are shown in the lower line. For the recorder, we have essentially only one sinusoidal line. It looks almost like sinusoidal as you look at the upper trace. That is proven by what we see here. Recorder has only one frequency, one sinusoidal function, describes the whole sound of the recorder as it comes from the recorder. For the tuning whistle, on the opposite, you have these strong structures here, and not to really expect it. Well, in fact, one can expect it then. What you see here, the tuning visual spectrum, and the places where we have non-zero amplitude or intensity are indicated here by these lines, and they come in equidistant positions on that scale, where we plot the intensity of this sound as a function of the frequency. And finally, also for the guitar, the same. Here we do not have many higher harmonics, at least in that picture, not. And you see this is more smooth also, the trace here. So that we can retreat, so to say, to the Fourier analysis in the description of all these sounds. At least it is a very important quantity which we have to consider, and helps also to understand the music. Okay, let's go to the next. Okay, to give you a better feeling what that means geometrically, these waves and the higher harmonics and overtones, that is shown here, for the example of a guitar string, where you have the ground tones in the upper case, that is the ground tone. You have simply an oscillation of the string, like something like that. The strings, of course, much faster than I show it now here, with the frequency of the sound itself. That could be something like 100 hertz, typically, for a guitar string. But the higher harmonics can, in the same picture, described by additional nodes which we have when the guitar strings vibrates. So we could have in the middle of the string, we could produce a note that can be done, in fact, by putting slightly a finger onto the middle of the string while you're playing it, and then this note persists and the frequency is doubled. Then we have other higher harmonics, as you can see here. We can have the notes at 1/3 of the whole length of the string. We can have then notes every quarter of the length of the string, and so on. That is the picture of the higher harmonics. Now, how it is also related to the Fourier series. The frequency distance between each of these patterns would be the same, fulfilling Fourier's theorem. Okay, now usually these are the kind of vibrations which you hear when you play a guitar or a string instrument. But our recent interest developed in extension of this picture. What is not shown here, and also hardly ever played, is the so-called longitudinal modes. I should mention one more thing here. We have a transverse oscillation of the guitar string here. So the guitar string oscillates like this. When this is the length of the string, the guitar string oscillates like this. And comparing with the propagation direction, it is so-called a transverse wave, because it oscillates transverse to the propagation direction. And for a standing wave, then this motion is back and forth and back and forth. You can, so to say, not escape, because it is clamped on both sides on the guitar. Okay, this is now the reason why you can hear this sound, because it generates a pressure, an air pressure on whenever it has its maximum amplitude. It oscillates in this direction, then it presses the air on that side to where it moves a little, then it moves to the other side, presses the air on the other side, and this pressure that generates a pressure wave in this way, and due to this pressure wave, which reaches also our ears, we can hear the sound of the vibrating string. Okay, And there is in fact also shown down here in that picture that is meant to be on the lower side. I hope one can see that properly. I think so, one can. On the lower side you see again the vibrating string with the ground tone, with this oscillation. You just repeat it here. And what you see in these bars which move up is the pressure of the air, the air which is pressed, that is meant to be by these patterns which move upward. And so it reaches our ear due to this mechanism, and we can hear the vibrating string and the sound of the string. I'm making such a point out of this because now we can also look at another wave which is very similar but also rather different, and that is the following. Let's come to the next one here. Now I draw again here a string. Is this blue horizontal line interrupted by these bars, by these vertical lines, and that is supposed to be a longitudinal wave. Now I can also show it this way. Suppose the wave travels in one direction and we look at the individual oscillations of the particle inside that string, then they would do something like that. That would be the motion in that string. And this is called the longitudinal mode because the extension, the elongation, or is in the same direction as the propagation. It's like this, and the propagation is also like this. So therefore, that's called a longitudinal wave. Now, from what I just said you before, we would not expect that we can hear that, because it does not compress the air on both sides. The motion is such that the motion always stays inside the string, inside that structure, and we would think we cannot hear that. And in fact, one can hear it only very faintly, not very loud. But recently, a group in Tokyo has looked into this and developed even a music instrument, or I call it always a silk organ, because it consists mainly of silk wires which can be brought into oscillations, and one needs special tricks in order to hear that. That special trick is also indicated here. It's that yellow cup which you can hear, which you can see here. The cup is also vibrates when the whole structure here, that string vibrates in the longitudinal mode, then the cup also starts to oscillate in the same way. And here we have an air, at the end of the cup, we have an area by which the air can now be compressed or decompressed while it oscillates, and this way one can hear that. Now, we would like to demonstrate that to you, and now we need two strong gentlemen to hold the silk wire. Okay. That is supposed to be an octave. I think one can notice there's a difference, and one can control that and produce a sound. Yeah, very good. Very Very nice concept, yeah. And maybe most of you know that from the children's telephone. As children, we played with such. Now there's development underway to make a music instrument out of it. And in Tokyo, they have already a big hall. They have many of these wires, and I call it always a silk organ. Okay. So far to the longitudinal mode. And an impression of the silk organ you also get here. There's many wires, many silk wires, and in addition these cups so that you can get the sound out of the silk, otherwise it would, so to say, remain all the time only in the silk. Okay, coming back now to the transverse mode, the transverse oscillations of strings. I included that here, which is supposed to show that you can influence the sound. I don't want to go in too much detail of that, but you can control the sound, a special sound of a string on a guitar. In fact, I can demonstrate it here by picking the guitar on a special place. So when you pick the guitar here, you have a more warm, smooth sound. When you pick the guitar more on the one side, you get a stronger, hard tone. That musician can make use of that, of course, to influence the character of what he is playing by the kind of sound. Okay, that is shown here by means of higher harmonics, where the spectra of the higher harmonics in the Fourier analysis are rather different, whether you pick in the middle or you pick on the sides. Okay, let's go to the next one. Oh, I think we can skip one. I didn't look into that much. Yeah. Okay, now come to the key question, in fact, with which we started, and that is, when do two sounds separated by interval sound smooth and harmonic and nice, and when this is not the case? When do they sound dissonant and rough, and so at first we would not think this is a very nice sound, but I'm a bit hesitating at the moment because I have difficulties by saying a nice sound and an ugly sound. This is very not objective, very subjective. And in fact, if you heard a music piece consisting only of very smooth and sounds, you would probably be bored after some time and you wouldn't find that very nice at all. The dissonances belong to the consonances, like the pepper or the salt on the bread. Only both together give a nice music. So with this precaution, I talk now about dissonance and consonance, and we ask ourselves, when do we get either? I can demonstrate a little bit on the guitar. I think that's it here. So this is what I mean by consonant. Instead of making many words, I simply let you hear that, and this is consonant. Because as I said, it's difficult to explain these words. But of course you want to hear now the difference. What is there not consonant? Then we play this one. thought to be dissonant. And I think you will agree that this sounds certainly more rough, or in a way also not so comfortable as the first one where we had this. Okay, now Hermann von Helmholtz, who lived around 1850, got involved in that problem and found the following relation: when does something sound more consonant and more dissonant? And this is what I would like briefly to explain to you now. Let's take two tones, just separated by an interval. And we have, for example, in the lower trace, the Fourier spectrum, all these Fourier components, intensity versus frequency of this of the vibrations of that sound. And now we draw a line to another sound, like, for example, here you can take the G. This is the same Fourier spectrum of the G. The frequency is given, by the way, here. And we can see that there are many coincidences. For example, at that frequency here, we have a vibration of the C, C3. But we get one here for the G. So the G and the C have a common higher harmonic at this frequency. And then you can also look at many other places. For example, one can repeat that. We started here. Wait a minute, I think I do that. I put it over to here. So here was the first coincidence between C and G. Zeig's einfach mal. Den hier, den. Yeah. So that is the first coincidence. No, a little bit over here. And then there is another one here. And then repeats itself. So you go 2 steps on the G scale here, and you get at the same time 3 steps on the C scale, and you have a coincidence. So here you go 1, 2, and here on the C you go 1, 2, 3, and get the coincidence in the higher harmonics. That is along the whole series of C and G. You find that again and again, and that is, according to Helmholtz, then the reason why the C and the G in that case sound nicely together, sound smooth, and he calls it consonant. Whereas when you have another case, I will show you maybe on another graph, other cases where this is not the case, where we do not find such coincidences, only very few or none at all, and that is interpreted then as dissonant. So that is the reason why some intervals sound consonant and others sound dissonant. Okay, if we can go to the next one. Okay, here, nein, nochmal zurück. Yeah. Now one can look, for example, into a case, and you find very often that when you play 2 sounds, 2 tones which are only half a tone apart from each other, So for example, how should I say this? Yeah, for example, these two. And I play them together. Yeah, this way. So that sounds consonant. Sorry, that sounds dissonant, somehow odd or rough. And for tones which are only a small interval apart from each other, this is very natural, because look at this example here. I have A on the lowest trace, I have A sharp on the next higher trace, and the displacement, because this tone is a little higher than the A, the displacement of the harmonics is only slight. So now you would have to, so since you don't have a coincidence here, and the increase, relative increase from one to the other is only small, you would have to go a very long way out until you find again a coincidence. That comes from because the increase here is only slightly smaller than in the other. So that is also a typical example, and most, maybe all, of halftones intervals sound dissonant. So that would be the explanation for that. Can I go to the next? Okay. And here we have this, I said already, tritonus. The interval C, F sharp is a so-called tritonus. And this is here, these for comparison, these two traces, F sharp, we call it in German Fis, and C form the tritonus, and you see you have only one coincidence here, and even that is probably not systematic. These, when you don't tune the string very exactly, then you can get also spurious shifts. So, but at least there is only one coincidence here, it seems so, and that is the explanation for that tritonus between F sharp and C. And only very near to that, you have, instead of the F sharp, you have the F. This is a clean chord, fourth, and that sounds in fact quite good. So you go only half tone away, and you have the tritonus, maybe demonstrated again here on the guitar. So here I have the C, and now I play the F sharp. Okay, I can think you can hear the dissonance in the tritonus. The tritonus is very often used in movies to accompany a horror scene that makes it even more horrible, like if it was without the tritonus. Okay, next please. Oh, this is finite sampling. I want to skip that. Next, please. Okay, this, what I just demonstrated to you, when we have that case where we have a halftone interval, then, and the increase on one string is only slightly larger than on the other string, then you have the same situation that you have in a moire. In a moire, you can also generate all kinds of patterns by having two barcodes, for example, behind each other, or two fences behind them, and In one case, the period is a bit different, maybe a bit larger than in the other. Then the increase is always smaller, and until you get the next area where you can look through the structure, takes many steps. And that is the same situation when you have a dissonance. So the mores, in particular when these areas where you have the light shining through are large, when the distances are large, is equivalent to a dissonance in the acoustic area. Okay, let's go to the next. Bitte? Aha, ein Lied. Yeah, Keiko just decided that it's now time to sing again a song, and why not? So, yeah, so let's do the song. And the motivation now to have at this place this song would also be the interval which we use there and the chords which we use there are all in agreement with the rules which I established up to now, which come from Hermann von Helmholtz.
Dort nieden in jedem Holz. Dort nieder in jedem Holze leiht sich ein Mühlenstolz. Was führet es seinem Munde von Gordo ein Ringelein?
Now, we would like to make some remark about singing and singers and talk about the vocal tract, which is, so this is Keiko's main occupation, to sing. And it's interesting to look at the vocal tract and what particular aspects there come then concerning the music which we produce with the vocal tract. And one of the things which are very interesting is that it seems that singing, at least with a very wide volume of different sounds and pitches and so, is restricted to humans. Our vocal tract has been, during the time, changed obviously in such a way that it made adjusted to singing. Singing seemed to be a very important occupation, and we adjusted in a way in our evolution towards singing. We changed our vocal tracts in such a way that we can better sing. That was not for free, that cost something, and what it cost is that what's it called? The vocal fold is here, and the larynx is here, and the vocal fold is the one where you also breathe. You breathe through the vocal fold when you sing and breathe. Singing and breathing is very much related. You mostly sing only when you breathe out, of course, not when you breathe in. So there's a strong relation. But in our case, the opening where we eat is very near, and that causes sometimes a problem. For animals and for primates probably the situation is a bit different. This opening where they eat and drink is much higher up, and so they can in fact drink and breathe at the same time, which we cannot. But the point is that our vocal tract has been changed in such a way that we are adjusted to singing. At one point, so to say, mankind decided we would rather sing and be careful when we drink and breathe, but singing is for us so important that we try that. Okay. So in order to demonstrate what's going on when we sing, one has to extend now the experimental possibilities as far as I show them up to now a bit, and go to so-called sonograms. What I showed you up to now was on one axis, for example, the intensity of a sound, and on the horizontal axis would be the time. That would be when we show a wave, then we would use this display. But the other was that we have frequency on the horizontal axis, and again intensity on the vertical axis, and that is when we were talking about a Fourier diagram, and we use this kind of display. A display by which we can now study better, or maybe only at all, the singing voice and the sound of the singer, or also speak, of course, speech, is a sort of called sonogram. Let's see if we have a picture of a sonogram here. No, there's more details now. The vocal tract here. The vocal tract shows, what is that called? I forgot the name. Yes, the trachea. Is this a trachea? Yeah. Here you see the trachea, and the whole singing is a resonance phenomenon. The trachea can be closed quite to a very small slit, as shown here, and then you can press the air through that slit and gives the sound. But the real strong sound which you hear from a singer comes from the resonance phenomenon. The whole inner part of the mouth and gets into resonance with the air which is inside, and that gives the loud sound for a singer. Okay, let's go to the next. Again, next please. Oh, I don't know why I put that here. No, we can skip that. That we saw already also. Okay, so yeah, so I would like to discuss now the left-hand part of this picture here. You see what is plotted is in the vertical axis, you have here the pitch of the sound, which you can record with a microphone or so from a singer or a music instrument. You see the pitch, the vertical direction. You see the frequency. Oh, wait a minute, is it time? No, the time on the horizontal axis, and you see in an axis perpendicular to the plane of the drawing indicates the intensity of the sound. So if the sound is strong, so that is indicated then in a way by the colors which you can see here. When it's the white color is being used, it's a loud sound, and correspondingly for the other colors is the color code for the strength of the sound. So with this we can now investigate the spoken word, or also the singing, and learn something or use it still in another way. Next please. So here we have this for the investigation in speech recognition, the spoken sound. As the speaker speaks, the time runs, so there's only for 2 seconds recorded here. And vertical is the pitch of the sound. And you remember the Fourier components, that they are equidistant, as I showed in the beginning. And that shows up in these patterns here. I always call them zebra stripe pattern. In these patterns, there shows up this fact of the Fourier components which are equidistant. you see these patterns like a ladder, and that comes from the higher harmonics of a certain sound. So that makes all somehow sense, and can now be used to record a voice, and then by means of electronics you can then also transmit that, change that into written letters, speech, from the evaluation of such patterns in the sonogram. Okay. Yeah, and I have in fact such a sonogram for the various cases here, and we can let it run. Hopefully it works. Gehen wir mal hier raus. I have to make slight changes now on the computer. Und wenn du draufklickst.
We play one more the folk song of Germany. Drunten im Unterland, das ist halt fein. Drunten im Unterland, da ist halt fein. Ich doch alleweil runden Gottes Blut.
Dr. Grünberg, if Helmholtz is right that our experience of consonance and dissonance is largely due to the coincidence of harmonic partials, why is it that we seem to experience consonance and dissonance, or let's say dissonance, when we're listening to combined instruments that don't really have many harmonic overtones? For instance, a trio of flutes together will not have many overtones. Each instrument will not have many overtones.
Mm-hmm.
And as a result, we would expect that they won't have many interlacing or coinciding overtones. And yet it seems that we experience something like dissonance if they're playing a tritone together, for instance. If Helmholtz is right, why would that be the case? Is there more to it than that, or?
You can only guess. I mean, when you have small intervals, like, then Helmholtz suggests still another mechanism which comes from beats. When you have two sounds like a half tone near to each other, then you generate mostly beats, variation of the volume. It's not a new frequency, it's a variation of the volume. And when you, for example, generate beats with pure sinusoidal tones, then they're very strong. And when the frequency difference, for example, would be on the order of a few 10 hertz, then it gives you a very strong rattling sound, like a motorbike.
So the beat frequencies give rise to the sense of dissonance.
So by this I want to say there are other possibilities also to get this dissonance, so-called dissonance.
Maybe it occurs to me that maybe we actually do hear dissonance more intensely between stringed instruments with many harmonic overtones relative to flutes playing together as well. I mean, one does seem to, the group of strings would seem to give rise to more intense dissonance than a group of instruments. But they do seem dissonant, and it's interesting. Question is, did Helmholtz talking about acoustics, did he also talk about the cochlea, about the auditory
Yes, as far as I can see, I read part of his book, and that, he discusses cochlea.
That's from the physical forms that are transduced. That's the other part of the story, I guess. Everything that happens from the tympanic membrane in.
One could, of course, also speculate. Sometimes you have sounds which seem not to be really there. They are virtual sounds that if, for example, a higher harmonics is formed in the cochlea, in the ear, that when you have a strong excitation of these hairs in the cochlea, and then you could come to higher harmonics also in the motion of these hairs. So they could be produced there in the ear itself and not already outside.
Such as with the ringing in the ears or tinnitus or something where it's
Yeah,
actually
the ringing problem. Yeah, a ringing in the ear, yeah, would be the same, yeah.
How much of this is just socially we're accustomed to the normal scale? In other cultures, they have totally different scales, totally different harmonies, and apparently like their kind of music. I don't. What about
Yeah,
the third?
there are certainly other cultures and other understandings of music, but my interpretation of all of this is that, but there are also sounds which seem to be common and which we classify also in the same way worldwide. And it's always said when you have you sing a fifth quint that carries much further than some other combination of sounds. And we're always talking about the people in the Alps who wanted to communicate from one alpine meadow to the other, and by yodeling and using these they got further and it was easier for them to communicate, and that helps also in the evolution. So you could also say people who doing this have a better chance for survival, and they communicate over a long distance, and that is a practical way to get further in your voice, to use such intervals when you want to communicate.
The slide I'm thinking about is the one that compares the frequency spectrum of C and F against C and F sharp. And my question, I guess, as you find that slide, relates to the difference between the waveform for the F and the F sharp, because I'm wondering why it appears that the height of the peaks in the F sharp seem to vary more than the F. And I was just thinking that the F sharp peak that is above the third dot in the bottom is much higher than the surrounding peaks, and it lines up precisely with where it is exactly halfway off between lining up with the F. So I'm just wondering why with, I'm a music student here, so why with equal temperament, which sort of claims that no note is any different than the other you can play in any key, so F should be no different than F sharp. If you're playing in F major, F sounds fine, and F sharp in F major should sort of have the same properties. So why it looks like inherently the F sharp has sort of more variation in its peaks than the F does alone. So I was just wondering if you could speculate possibly on the difference of peak height that is found here. Thank you.
I did not watch the screen while you were talking, so I probably lost a lot for that. But I think a reasonable answer for you, the first part of what you said would be, I think one can say it's sort of arbitrary about the scale, what is F sharp and what is F. It could also be the other way around. It's also in nomenclature. What counts for the tones we select, or which we call F sharp or F, essentially they come always from natural tones, but then there was this Bach and colleagues invented the well-temperatured scale, and which is full of compromises, but finally came up with a solution for new sounds, which finally developed from the natural sounds, which sounds also good for our ears. Although many people say when they hear natural tones, it's much nicer, it's much cleaner, and so in a way, I think the answer would be this sort of arbitrary. What is F or F sharp is sort of arbitrary.
It's interesting that with equal temperament, we seem to have some tolerance for out-of-tuneness with equal tempered instruments.
Yeah,
So
yeah.
to a degree of tolerance, we still will really hear something that's consonant, even if these kinds of coincidences aren't very exact. Well, thank you very much to both of our distinguished guests this evening. Interesting to see these kinds of interdisciplinary interactions and the kinds of things that musicians deal with on a daily basis, but when we're provided with an acoustical or psychoacoustical background of this kind, it makes us feel that maybe we actually know what we're doing some of the time, but know that we're interacting with the natural world in this way. Thank you very much,
Thank
Dr.
you.
Greenberg. Thank you, Keiko, for your presentation. And I understand, Mr. Dean, we have a reception, a polite reception and refreshments in the foyer. Is that right? Immediately, we could probably interact and ask further questions. Thank you so much again.